So what I'd like to do is to split the class time today into two parts. The last lecture I had, I kind of had the feeling like I was talking too fast and not getting you to the bottom message of this. And as I mentioned before, it's the case that I was so happy that I had my lecture all done, but the way this lecture has usually happened in class is I walk people through the Mplus printout. So at the end of the day, what I have here is an example of different things that you can do with exploratory structural equation modeling that will allow you to fit a multi-group model and combine the idea of an exploratory factor analysis with a multi-group analysis. And this little table is the bottom line that I'm going to make some assumptions across sex about whether things are variant or not variant. And at the end of the day, we landed on this model in which the factor loadings and the manifest variable intercepts are the same across groups, but the factor means are different and the error variances are different. And in order to identify the model under that strategy, I can get away with the factor variances all being one and the factor covariances all being the same across men and women. I don't necessarily have to do that. I could, for example, let the variances, the means and variances be different across the groups. But this is the one we landed on. So let's now step back and take a look at this in Mplus land, because Mplus is the only platform you can do this on. Here's our Mplus program, and just to orient a little bit, because it's been a while since some of us have looked at Mplus printouts, we say, here's our title for our model, and here's our data, and here's the names of our variables and the variables that we wish to use, and what our missing data code is that's present in the data. It can be a dot or a star. And this is what tells Mplus that we have a multi-group model. So depending on in the variables, sex, one is female and two is male. One little wrinkle that people did talk about is that if you've got character data inside of Mplus will not read that. In other words, you can have character data in the file, but you can't read it in as a variable. So here's where things get a little bit strange, that if we were just doing a straight exploratory factor analysis, we would just say the analysis is EFA and say how many factors we wanted. But if we're doing an ESEM, we need to put in some code in here that's going to tell the program what we want to do. So in here, the model statement, this first thing is going to contain the definitions of the factors that I have that are going to be kind of the default. So women are the first group here. So this is going to describe the factor models that I have for just the women. And downstairs, if anything else new happens for the men, that's down here. So the easiest, first of all, this is code you can steal. And I don't think that there is a lot of stealable examples out there of this type of thing. But the second thing to do is this little bit down here of check one. Check one is your friend in this situation for understanding what you're holding the same and what is different. So let's come downstairs and take a look at our check one. So here's the code for all of the free parameters in my model. And this reads just as it would for a confirmatory factor model. Here we have new. New are going to be my intercepts for the manifest variables. And we see that for the women, I've got 20 variables and 20 parameters. And downstairs, I've got my factor loadings here. Now, prior to rotation, Mplus is estimating all of these loadings. So that's why you see for this first factor, all 20 of these have loadings. And then in order to extract a second factor, I'm going to be extracting these loadings, setting this first loading to 0, And the third one is the same song, second verse, everything but the first two and everything but the first three. And this is going to form the unrotated factor loading matrix that I'm going to be rotating to a Mplus defaults to a geomin oblique rotation. Okay. It's Friday. Feel free to interrupt, but if not, I'll keep on going and hope that I'm going at the right pace. So down here we have theta. Theta are our error variances. Now, as we'll see as we talk through this today, I can, if I want, put in some error covariances here if I think they're kind of reasonable. So, you might say maybe some of the reasons that this variable is associated with that variable is not just due to the presence of latent variables, but is due to the fact that they share correlated errors. And that's all of my 20 free parameters here. Next comes alpha, and these are my factor means. And I see zeros here. So that's telling me that for the women, the factor means are a fixed parameter and they're fixed to their default of 0. Beta are paths from a latent variable to a latent variable. You could put some of those in if you wished. In this model, I didn't, but that's why all of these are zeros. And psi is my variance covariance matrix of the factors in the model. Okay. Now we turn to the males, and here is where we start to see, oh, what about the males is free? The last free parameter I had for the women was 114. So anytime I see a number bigger than 114, I know I'm going to be talking about something that's different for the men. Well, right away, here's 115. The manifest variable intercepts for the men in this model are free to vary. And down here, here's my loadings, 135. So we know in this model that the factor loadings are free to be different with men than women. And down here are my error variances, and that's 209, bigger than 208. So all of these are free. So in a nutshell then, this first model is saying, yeah, women have reasons for drinking and men have reasons for drinking, but there's nothing about the factors that are involved there that are necessarily at all similar. They could have completely different rotation. They could have completely different error variances. They could have, the factors themselves could be correlated differently. So that's the model in a nutshell for this first model. So let's zoom back up here and take a look at our rotation. The default rotation is geomin, and you could do any other rotation you would like, Promax, Varimax, bifactor, and so forth. And it's an oblique rotation, meaning that our factors will have correlations. I was talking with somebody and they didn't understand this part of the printout. So let's talk a little bit about this. One of the things about this model is we are doing maximum likelihood estimation. So anything that comes out of Mplus is going to be different than anything that comes out of FA and R, and to some extent, the factor analysis programs in SAS and SPSS, because it's going to do full information maximum likelihood. This little bit here are the missing data patterns, and you'll see down below a count of exactly what kinds of missing data patterns were present in the data. And this is another count of all of the missing data patterns that happen for the men. The next part here is coverage. Coverage is a fancy word for the proportion of pairs of variables in here that are non-missing. So in this data set, the amount of missing data is very small. It tends to be the case that if you filled out some of these questions, you tended to fill out the rest of them. Every now and then people might, not answer a question here or there. And it gives you that model separate, those coverage statistics separately for the women and for the men. And then it gives you the summary statistics. The thing that you're looking at here in your summary statistics is it might help you to know a little bit more what a problematic variable might be to look at the skewness variables. So this item is, for example, negatively skewed. If you find that you have some model fit, one of the several things you can consider is to think about maybe rescaling that variable. And that's where the pair plot and core plot procedures became useful, because you could see if a lowest regression would give you a straighter line. And down here are our fit statistics. So this is the BIC value for this. And if we come back to our SEM book 1, these are the summary statistics that I pulled off for you. For the BIC, a lower number is better. Coming back to Mplus. And here we have the factor analysis results. So this has been rotated. So the reason that you're going to see something that looks kind of sort of like simple structure is it has done a geomin rotation. It took that original, what we would call triangular decomposition, where for the second factor I set a loading to 0 and the next one 2 to 0 and 3 to 0, and it rotated it. And what you see over here is the statistical significance associated with each of the loadings. And same song, second verse for factor 2, factor 3, and factor 4. And down here we have our covariances between the factors. And our variances are fixed at 1 because all our loadings were free, and our intercepts are freely estimated. Therefore, our means for the factors up here were all fixed to 0, which is another point. And when we talked about multi-group models, to identify the model, if you want to have the factor mean, you're going to have to at least set one of the intercepts of the manifest variables to 0. Or if you're doing a growth curve analysis, you might set the intercepts to be a common value of a shift, and then you can estimate a factor mean. Same song, second verse for the men, and you'll notice that none of these numbers are the same across men and women. So for this first item, I have 797. For this first item up here, I have 854. That's part of what we talked about in terms of free parameters. So that's model 1. And downstairs, you can have modification indices that will give you some clues about slings you could draw or arrows you could draw that might improve model fit. So for example, item A and B, which has to do with parties, that has a relatively large modification index. And you might want to consider maybe freeing that for the women. And downstairs, we can come to the men. We don't see the similar modification index for the men. So, those are some a posteriori, post hoc modifications you could think about if this is a model you wanted to land on. But as we've seen from the table and PDF, model 1 was not the one we landed on. So I hope like I'm doing this in a slow fashion. Are there questions about this bit before I put it away and go to model 2?
Really quickly, on the modifications, how would you go back and modify that? So
Okay.
you see those, and is there a certain number that you're looking for, or it's just a large number?
The modification, well, all right. So the fancy pants answer to that is the modification index is going to be a number that's going to be different depending on the sample size and the characteristics of the data. So the default for Mplus is the number 4, but I have no idea why that is any better than any other number. And what you see over here are some expected differences in the change of the model if you free that parameter up. So, this one is kind of sort of substantial. So it's basically kind of an eyeball thing. And you have to be kind of careful of making modification indices just on the basis of statistical significance. It has to be something that you could tell a reviewer, well, looking at it now, it's one of those, what is that commercial? Wow, I could have had a V8 moments. These two things probably are related at the pairwise level. But to get to your question, say I wanted to make this change, well, what I'll do is I'll come back up, I'll copy that, come back up here to my program. And inside the first model, I can say, estimate me something that's free. And then if you didn't want to have that happen in the males, you'd come down here and then say, fix that one at 0. Because if you don't, it's going to default to letting that error covariance be there. So it's pretty easy to do. And later on, I think it's in like model 4, there was one that kind of sort of gets close to, maybe you want to put in a pairwise, that's an example. Okay, that's a good question. More things? Because the males are a little bit different. In addition to this, you might get some individual, let's think about maybe allowing some of these things to be different for the males. But model 1 is just kind of this agnostic model of everything could be different. If we take a look at model 2, here's what our code is. So notice that the only thing that I've got going on here is the intercepts here for the men, and everything else goes to its default. Now, this is kind of a nice way of doing this inside of Mplus, but let's go back and come downstairs to our Tech 1 and really understand what's fixed and what's free. So here we have the women again with their intercepts and their loadings as before, and their error variances. And that comes down to 114. And I didn't estimate any means for the women, and I don't have any assumptions about the variances and covariances. I'm going to rotate later to that. But now downstairs, my last number up here was 114. Well, 115 tells me that the manifest variable intercepts for the men are now different. But look down here, what happens? I've got the number 21. In other words, the factor loadings are constrained to be the same across men and women. So when I rotate, after rotation, I'm going to see the same factor loading for the men as for the women. And downstairs here, well, now I'm back on the train writing again. I have 135. The error variances for men are different than the error variances for women. And again, as before, I've got means fixed because I had to, because the manifest variable intercepts were freely estimated. And downstairs here, I've got different variances and covariances among the factors for the men. So that's what's going on. It's the case that the picture in terms of measurement invariance is the same for men and women. In other words, the factor loadings are predicting manifest variables from a factor are the same across the two groups, but the amount of latent variable variation and covariation is different, and the amount of error variance is different. So we can zoom upstairs here and see if all of this is in fact so. Here's our covariance and our summary statistics and our things that are in the table in the PDF. And downstairs here are our loadings. So 848, I should see as the first loading for the men as well. 848. And the variances of the women are 1, and the means are 0. And here are the variances and covariances among the factors for the women. So coming downstairs to the men, here are the variances and covariances for the men. and here are the variances for the men. So men are allowed to have less variation in their reasons for drinking, except for this last factor, which has to do with how it tastes. So it seems that the men have a much larger, variance on that particular factor in their reasons for drinking. Well, these numbers here, 0.90, 0.99, 0.976, those are pretty close to the women's variances. So maybe it's a more parsimonious model to ask the question, maybe the variances are the same across men and for women. And then downstairs here, we see the residual variances are different than we had for the women, which is further, generally speaking, I just don't know, men are just messier relative to women. That it's often the case that error variances for variables in general are poorer for, are larger for men. They provide you with less reliable information. Now, one of the things to keep in mind is that if you're looking at standardized values, those standardized values are going to be giving you the same pattern for men and women only if you're constraining the error variances and the factor variances and the loadings to all be the same across the groups. So the standardized coefficients here are somewhat useful because they're going to tell you what the largest standardized effects are, but we can't really report these numbers in our final model if it's going to be a multi-group model, because even factor loadings that are constrained to be the same across sex, which they are in this model. We'll take a look at the female one, 0.969. I can shoot down here to the men, and that's 942. In other words, those things are not going to be the same because the error variances for one thing are different and the factor variances are different. And that's our model 2 here. Okay. Well, stop me before I teach again if there's questions. So if we turn into model 3, let's shoot down to our, all right, so slow up and look at this first. Here's our model. It looks like, there's nothing downstairs particularly coded for men. The only things that are a little different is that we mentioned the mean here. And I have to confess, I don't really, like the way they set this up in terms of syntax and how you have to write the defaults, but your safest thing is always to come down to your check 1. So here's the women as before. Here's their loadings as before. And we know we have 114 at the bottom. Well, here's the men. The men's intercepts are the same as the women. Here's the loadings. Those are the same. Here's our thetas. So the error variances are different. Downstairs, because our values are, we're writing the defaults, the means are assumed to be the same across men and women. And then downstairs here, these numbers indicate that the variances and the covariances are going to be different. And so that was model 4. And that was the one we landed on. So if we come back to model 5, that has a bit of a wrinkle in it. So you'll notice in here that it looks kind of like Model 4, except we have these lines of code in the overall statement. Well, putting in a left paren, the number 1 on a right paren, gives the covariance between factor 1 and factor 2 a parameter name. And because that has a parameter name, and you're coming downstairs and just writing the defaults on the male model, this is going to correspond to constraining the covariance between factor 1 and factor 2 to be the same across men and women. So if you, for example, wanted to constrain some of these to be the same and some of them to be different, you'd come downstairs and say, inside the male section, you'd do that and remove the parameter name. And that would then allow the covariance between factor 1 and factor 2 to be different for the men than the women. But this strategy of making a cross-group constraint by giving it a parameter name is the way that you step yourself through the various other invariance hypotheses. So if we come downstairs and look at our model, here's the intercepts, here's the loadings, here's the error variances, and here's our means and our variances and covariances. And downstairs for the men, here's our intercepts, are the same as for the women. Here's our factor loadings, same as for the men and the women. Here's our error variances. And that's what's, that's the thing that's different. And our variances and covariances in here are all zeros. And the reason that they're all zeros is because they were zeros for the women. So that's the way that we're saying that the variances and covariances are constrained to be the same across men and women. So if we come upstairs to this and look at our answers, here's our loadings for the women, geomin rotated, and downstairs, here's our loadings for the men. And all of these by statements, like factor 1 and factor 2, is a correlation of 0.359. And if God is in heaven and all is well with the world, I come upstairs to factor 1 and factor 2, and I've got 359 there. All right? And if we're considering model 7, notice this has the same code for the variances and covariances being the same, but it's saying, oh, and in the male group, I want to constrain the means of the factors to be 0 because all of these intercepts are free to vary across men and women. And if we come down to the technical output, that's the same thing that we see before. Here are my intercepts for the men all being different numbers. And because all of those manifest variable intercepts are different numbers, I have to make the factor mean 0. Right? So inside of this, at the top, there was a little gloss. If you're running this model based on the modification indices, it seemed that some of those item T and item S in my little survey thing looked like they were an error covariance I might want to add. And further, the modification index looked a little bit different, so I might want to add a slightly different error covariance for the men and for the women. And that's what this commented out code would do if you remove the $sign and ran it again. But those are small refinements. I mean, the nice thing about this, to kind of wrap up the presentation, is this is a lot nicer than the models you are forced to report if you're doing a study of anything that possibly has gender differences in it with any other software platform, because under those other platforms, the only things you can do is run an exploratory factor analysis here, an exploratory factor analysis there, and kind of talk in a discursive fashion about how similar the numbers look, maybe via concordance coefficient or eyeballing it. And this is rather elegant in that at the end of the day, you can say, actually, as loadings, these loadings are the same across the two, and it's the measurement error that is different, and that's why an exploratory factor analysis might look just a little bit different for men and women if you did two single group analyses. Okay, so I don't know. I think I'm doing a better job of explaining it here than trying to walk you through the PDF because it got a little hectic last time. But anything else on this?
This is helpful.
Okay, thank you. It's so quiet. It's like a Ouija board. Are you there? Is it okay? Are you pleased? Okay. All right. So in the time we got left, I want to talk with you about categorical dependent variables. And it used to be the first couple of years I taught statistics at Missouri, I would say, well, of course, we have to go through the theory and get all this rigor. And only then are you entitled to, do things the easy way. But, I'm 64 now. The easy way is inside of Lavon or Mplus, you will include a statement that says the following variables are categorical. Now, and what I want to caution you on that is when you tell a SEM program, this is categorical, by default, we're meaning that this is an ordered categorical variable, that there is, in some sense, some underlying continuum in the data. And the second thing, as we'll go through when I fill this in with the theories and the whys and the wherefores, is that when you're doing this model, it's probably the case that if you have a larger data set, you can treat this as categorical dependent. And if you have a smaller data set, like a few hundred observations, you can still perhaps take a variable to be categorical, but you might need to collapse some of the categories together. So the concrete, perhaps most used example is the 5-point Likert scale from strongly disagree to strongly agree. Well, it's impossible in your survey to get, 1.5 as a response. It's either going to be 1, 2, 3, 4, or 5. And secondly, there is probably nothing about that number, 1, 2, 3, 4, 5, that represents an interval scale. When we do standard structural equation modeling, well, yeah, we treat it as an interval level scale. And if you have smaller data sets, it's probably okay to do that. You probably will have a useful model. Nominal categorical variables, like, Andreas has one with country, or colors, things like that, that don't represent a continuum, are possible inside of Mplus. I don't think they're possible inside of Lavon, unless they've upgraded it recently and I don't know about it. But long story short, if you have a categorical variable that's nominal in level, all that the structural equation modeling program is doing in the background is making a set of dummy manifest variables. So having talked a little bit about that, let's talk about deep categorical variables and when they're a problem and when they're not a problem. Well, one of the main messages of my talking with you this semester is that everything that you know about in graduate statistics is a special case of a structural equation model. So thinking about a t-test, are men different than women? Are young people different than old? Or an analysis of variance, is counselor-directed therapy or self-directed therapy or a control group of read a self-help book, Are those things different? Well, those are categorical variables. When they're a predictor variable, that's not a problem. So, for example, some of the consultation I did this past year, the researchers had biological sex. They said, well, I can't put that in my structural model because it's only got 2 levels and it's not normally distributed. So long as it's exogenous, that is not a problem. The only time that categorical variables become a problem is when they are a dependent variable. And that's because in structural equation modeling, if a variable is endogenous, if it is a dependent variable, we are assuming that the conditional variance is normally distributed. So, and let's talk about at least 3 reasons why you can't use a binary variable as a dependent variable. First, the distribution of errors of prediction in a regression model isn't going to be normally distributed. Errors of prediction can only be 1 minus y hat, where y hat is your prediction, based on the other predictors you have, or 0, because your dependent variable can only take on values. And the second problem is that error variances in y as a function of the predictor variable are not homoscedastic. So a little bit of math nerdliness here. The variance of a binary variable is pi, the proportion of ones in the population, times 1 minus pi. So if the proportion of ones in the population is 0.5, the variance is going to be 0.25. And that's the largest variance you can ever have with a binary variable. If the proportion is 0.1, then the variance is only going to be 0.09. It's a lot smaller one. Well, let's carry this over to the case of a single prediction about a predictor variable. And there's a little bit of math there that I reference here, but the error variance is going to be my pi, my predicted pi, times 1 minus my predicted pi. This depends on the values of my predictor variable. Well, so as x increases, goes up or down, the variance of error is going to change as well. So, that's not going to work. So plugging in a couple of answers here, if I've got 0.2 and the regression weight is 0.3, the error variance is going to be this. However, when x of I is 1, I'm going to have this error variance. So depending on the levels of x that I have, variance in my y is going to be different, which is a violation of the model. And finally, if a dependent variable takes on 2 values, the predicted value has to lie on the interval 0 to 1. Well, it's possible in your regression model, since you're just using predicted variables, that you'll have a predicted value for somebody that's minus 0.2 or 1.1. I remember reading in the American Statistician kind of a funny little article that said, if 0 is being dead and 1 is being alive, is minus 0.2 a fate worse than death? You'll have predicted values that don't make sense. So the way we're going to get around this is by using something called a latent response variable. And if you read the literature, there's kind of some twisty little language about how people talk about it. You'll hear people say things like the latent response treatment or LRV models, but those are all different words for the same things. In a word, what we're going to do is we're going to fit a structural equation model to the data, and we're going to pretend that there exists some continuous version of the variable y that we're really working with, but that God has only given us values that are 0 and 1. And we can build our statistical model on the hypothesis that there really is an underlying normal distribution that reflects the categorical variable or an underlying logistic distribution. So I'm being a little slow here, but haven't lost anybody yet in class. So this pretend distribution that we're going to talk about, that we're going to call a latent response variable, we're going to use the word y star to talk about it. And as I mentioned, it's either going to, generally speaking in software, normal and logistic distributions are out there. Now, for reasons that we'll get into later, maybe that assumption isn't a good one. That, especially if you're looking at a property, an underlying distribution that's a rare event, you should be looking at something else. And for reasons that are a bit number crunchy and maybe not for the purpose of an intro ESEM class, the Gumble or log response function might be something you'd want to Google. Or if you are interested in professionally modeling something that's rare, like murder or odds of a psychotic break or other things that just a financial collapse, you probably then want to take a class in something called generalized linear modeling, which will be latent response variables where you can pick other distributions than the logistic and normal distributions. And I talk about that here. So, and to be reassuring, it's going to be fine at the end of the day. With very small modifications to your ESEM program, you too can model categorical dependent variables. So let's talk a little bit about this. And for some reason, people say it's helpful to start out with the simple things. Remember the normal distribution function. It has this little formula, and it's not important that you know this formula, but it is important that you think about some of the properties of it. The normal distribution can, in theory, go from negative infinity to infinity. And often in our work, when we're doing, say, a Likert questionnaire, we're going to assume that the particular normal distribution we're going to look at has a mean of 0 and variance of 1. You don't have to do that all the time. So if you're looking at growth data, for example, and you have a Likert question you asked at time 1, time 2, time 3, you can allow that normal distribution variable to have a mean that moves over time or a variance that increases and decreases. But for the moment, to keep life simple, let's just talk about the standard one. If you want the more complicated form of this equation that does allow the mean to change, it's this. So, this is the mean here, and this is the standard deviation. So that's what that distribution would look like. So, and here's the normal distribution, and it's our familiar little nice bell-shaped curve. Well, what do we got over here? This thing called the logistic distribution. The logistic distribution is kind of nice because it has a really simple form. I can take e to the minus whatever my y value is for a variable, divided by 1 plus e to the minus value and square that quantity. And if you plot this curve out from, minus 5 to plus 5, you'll get this little dotted line shape. And this model, this particular distribution does have a mean of 0, and the standard deviation is a little bit skinnier than the normal distribution. The standard deviation is pi divided by √3. Sometimes in software, when they're talking about this, they'll report scaling this by square root of 3 divided by pi, but that's just something you need to be aware of when you're playing with the software program that you have. And I mentioned that in a footnote. Mplus and Levon are just using raw logistic values, so you don't need to worry about that. So if you have a logistic distribution and you want to move it around with a different mean and variance, this is what the formula looks like. Right? This is, at our faculty meeting, our chair said, don't run class over. You're stressing people out, to the entire faculty. So this looks like about the right time to end this. The next thing that we'll do is talk about how we're going to take the binary data that we have, the zeros and the ones, and map those onto our logistic or our normal distributions. Right. So